I'm going to start discussing generalized coordinates. Okay, so generalized coordinates, okay? So imagine that we have a system of n particles. So that means that I have, n position vectors, I from 1 up to n, and I have k constraints. Okay, so that means that I have 3n minus k equals little n degrees of freedom. So these degrees of freedom are what I'm going to call generalized coordinates. Okay, so this I is going to go from 1 to little n. And these will be independent. And they are independent because I have already solved the constraints. Okay, I can move them in any which way I want, and they always satisfy the constraints because these are the independent coordinates that solve the constraints. That's the way it is. And so then, if the system is holonomic, the solution of the constraints is just a functional relation, right? So the positions of all the particles are a function of all these generalized coordinates, and maybe also time if there is explicit time dependence in the constraint or in the constraints, if there are more than one. In this case, there are k, right? And this is again true from 1 up to capital N. Now, how about the velocities? The velocities are the derivative with respect to total derivative with respect to time of each and every one of the position vectors. And so therefore, using the chain rule, we already discussed this thing. This is going to be the sum from j equals 1 up to little n, derivative of the position vector with respect to the generalized coordinate, times the derivative of the generalized coordinate, which can be called generalized velocity, if you wish, plus the derivative of the explicit time dependence. So this says that the positions depend on the generalized coordinates, but the velocities depend on the generalized coordinates as well as the generalized velocities. So there is this extra dependence in here. And actually, the extra dependence on the generalized velocities is given by this term. And therefore, we have a relationship, right? Because it says that the derivative of the generalized velocity with respect derivative of the velocity with respect to the generalized velocity equals the derivative of the position with respect to the generalized coordinate. Okay, and this is a very nice relationship that we're going to use. So we're going to frame it. We frame it because we want to remember it. Okay. Now, these I already said, but is there any question regarding this chain rule? Differentiation, any question regarding anything?
Well, yeah, just a thing. It's kind of stupid. At the beginning, you've labeled I for the degrees of freedom, but then you've labeled I for the number of particles. It should be J, isn't it, for the degrees of freedom?
Okay. So sorry. So yeah, I wasn't sufficiently clear. Okay, let's put a J if you wish. Okay. Is that better?
Yeah.
Here we can do the same thing. I mean, of course, you should realize that which letter I use to label things should not matter, right? I mean, as long as in expressions like this, I really keep a difference between J and I. I mean, here what I could not do is call this I and this I, but as long as here I distinguish between I and J is fine. Here I could call it J, I could call it K. I mean, this equation is also true if I write it like this. Agreed?
Yes, of course.
Okay, so this is what is called this when the index is summed over or the variable is integrated over, is called dummy, right? It doesn't say anything. It's dummy. So it's a dummy index. Okay, so we have this relationship, which is going to be useful, as I'm saying. And now we need to compute the virtual displacements, because remember, the work that we have to do now is we have to rewrite D'Alembert's principle in a useful way. And that's the way the Lagrangian function is going to come out, okay? So let us compute the virtual displacement, because that's something that appears in D'Alembert's principle. And so since R is given here, so we can just, also frame R. So since R is here, the virtual displacement of R is going to be the sum from j equals 1 up to n of the derivative of Ri with respect to Qj delta Qj. And this is what defines a virtual displacement, right? Because I'm bearing R without bearing the explicit time dependence, right? It's only Q that is moving here, okay? Now, why do I want, what is it that I want to do with this virtual displacement? I want to compute the sum from I equals 1 up to n of Fi times delta Ri, because that's one of the terms in D'Alembert's principle. So that's easy. So that's nothing but the sum from I equals 1 up to n of Fi and the virtual displacement that I just computed. So that is sum from j equals 1 up to little n, partial derivative of Ri with respect to Qj times delta Qj. And this I can always write as a sum from j equals 1 up to little n of something that I'm going to call capital Qj, delta Qj. And this capital Qj is, of course, the sum from I equals 1 up to n of all the external forces times derivative of Ri with respect to Qj. And this is true for j equals 1 up to little n. And these are called generalized forces. So once I know the external forces acting on the system, and I know the constraints, I know the generalized coordinates, and I can compute the generalized forces, okay? Now, so that was one term.
Can I ask a question?
Yes.
I'd like to ask what these delta Qj's are.
Well, the delta Q's are defined here, right? R depends on Q. Q, so imagine that you have, 25 of these R's, and you have 24 constraints.
I understand what these Qj's are. I don't understand what the delta Qj's are.
Is a variation of Q. So if you have that R depends on Q, you understand that delta R is. You vary Q, and therefore delta R changes, through the chain rule. And notice that the variation of R is a variation in which I have taken this time as a constant. So that's a virtual displacement. That's how we define virtual displacements. So that's a virtual displacement of R, and that's a virtual displacement of Q.
Okay. Thank you.
Any other question? No? If there is anything, you guys, are doing, the right thing. You stop me, you ask me, or you ask me a question, or you ask me to repeat something. Huh? There's no question about that.
Sir, I have one question.
Okay.
About generalized forces. Can you give some intuition how to think about these generalized forces?
No, because you see, these generalized forces are like the external forces. Okay. For instance, as an external force could be gravity, to say something. The generalized forces would be like the external forces if there would be no constraints. If the R's and the Q's were the same, which means that there are no constraints, then they would coincide. But the generalized forces get completely distorted by the fact that there are constraints. So I cannot give you an intuitive, picture of what the generalized forces are without, having an intuitive picture of what constraints you have in your system.
Okay, I understand.
Okay.
Yeah.
Now, so this was only one part of the D'Alembert's principle. Now we have to look at the other part. And the other part, if you remember, was the sum from I equals 1 up to capital N of P dot times delta R. Now remember that D'Alembert's principle was this minus this equals 0. So now we computed one side, now we are computing the other side. And so here we have to do a little bit of algebra. So bear with me, okay? Bear with me. We're going to go step by step. So this is the sum from I equals 1 up to capital N, the mass of each particle, the acceleration of each particle, times this virtual displacement delta R that I computed. Okay, actually here I forgot an index, because if there are n particles, there will be n momenta. Okay, now this is the sum from I equals 1 up to n of mi ri double dot, that's the acceleration, and times the virtual displacement that I just computed in the previous slide. So that's the sum from j equals 1 up to little n of the derivative of ri with respect to qj delta qj. Okay? Now, let us look at this part. I'm gonna, underline it in red. Okay? So we look at this part and we compute this term all by itself times derivative of ri with respect to qj. Okay? Now, this, because in R I have two derivatives, I can write it as a derivative of the whole thing times derivative of ri with respect to qj minus the derivative acting on the other term, d dt, derivative of ri with respect to qj. You agree with me, I hope, right? Any questions about this? So this derivative acting on these two terms, okay, has one derivative acting on the first term. That's exactly what I have on the left-hand side, times the second term. But in this derivative, I also have the first term times the derivative of the second term. And this I have to subtract so that, this equals that. Otherwise, it wouldn't be true. Okay? Any questions? Okay, so now we're going to compute this term right here. So what is the derivative with respect to time of the derivative of ri with respect to qj? Okay? Now, ri is a function, remember, of q. Ri is a function of q, of t, and t. So if I apply the chain rule here, this is nothing but the second derivative of ri with respect to qk and the qj that I already had, times qk dot, and then I sum over k from 1 to n. That's one term. And then the time derivative has to act also on the explicit time dependence. So that is the second derivative of ri with respect to time and with respect to the qj that I already had before. Okay, any questions about the chain rule? No questions? Okay, so now I can also write this thing because qk and qj are independent of each other, and because this time here is the derivative with respect to the explicit time dependence, it also, can be interchanged with this q. So this is nothing but the derivative with respect to qj of the whole thing, which is the sum from j equals 1 up to n of the derivative of ri with respect to qk, qk dot, plus the derivative of ri with respect to t. Okay? I can factor out this derivative with respect to qj. And, surprise, surprise, what we find here is the same as the velocity. This is the velocity that we had in the previous slide. Just look at this expression, dr dq q dot plus dr dt. Here it is, dr dq q dot plus dr dt. So it is the same expression. So indeed, this is the velocity. So what we find is that this is the velocity, the derivative of the velocity vi with respect to qj. So here we find another of these, it'll be another of these relations that is going to be useful. And so therefore, I'm going to frame it. Okay? Good. So now we can come back. Here we have the expression. This is the expression we were needing in here to compute D'Alembert's principle. Yeah? And this expression that we need on one side of D'Alembert's principle depends on precisely this derivative that we just computed. Okay, so we are going to input this term in here. This term here, this term, we're going to use it here in the next slide. Okay, so there we go. So we start. Derivative with respect to time of mi velocity. Before I had r dot, but that's the same as the velocity, times the derivative of the velocity with respect to q dot j. Okay, so this, let me go back. This is this, okay, this relation. But because of the previous relation, dr dq is dv dq dot. So this is dv dq dot j. And this is the thing that I'm going to use. Here you have it, dv with respect to dqj. Okay, minus the second term, mi vi times derivative of vi with respect to qj. Okay, so let me go back again. Right, is mvi and this derivative, which is dv dq. dv dq. So yes, so that's exactly what we have on the right-hand side of D'Alembert's principle. But notice the nice thing. Well, before we notice the nice thing, are you guys lost with these manipulations, or is there any question that you guys would like to ask? Anything that has to do with, you know, these replacements and things? So, I mean, I would prefer if there is no question that somebody says no question. So then I know that I can go on.
Okay.
Yeah,
John,
no question.
no questions.
And if anybody has a question, then please ask. And we can go back and look at it again. Any question or not?
No, no.
No.
Okay.
No.
Okay. Okay, fine. I mean, you guys have to realize that it's a little bit difficult for me to know exactly whether you're following a step by step or not, because I don't see your faces, right? When I see your faces, I can more or less guess whether you are understanding or you're not understanding. Of course, sometimes I also make mistakes, but now I cannot see your faces. So it's a good idea that you keep saying yes, no, and you ask questions, even if you think that those questions are naive. Maybe they are not that naive, okay? So it's worth that we keep, you know, communicating each other, that this is not a monologue, okay? That it's only me who is talking. After all, you guys are only 30 or 40, so it's much easier than, you know, in a class in which you have 100, which is also what I have. Okay, so everything seems to be okay so far, okay?
Okay, yes.
Okay, yeah.
All right, so now we're going to take this expression and we're going to rewrite it, okay? The first term, we're going to write it as the derivative with respect to t of the derivative with respect to q dot j of something, okay? And this something is going to be the sum from I equals 1 up to n of 1/2 of mi vi squared. So with this, I forgot here a sum. Huh? Here it should also sum over I from 1. Or if you wish, I'm going to do it in a different way. I'm going to do it the same way I was doing it. So let me just take out this sum. The sum is not there. It'll be there in a second, but it's not there yet. Okay? So what I'm saying is that this first term is this first term. Okay? Identically. If you take the derivative of something which is a square, you bring down a factor of 2. The factor of 2 cancels the factor of 2. And then you have mbi times the derivative of vi with respect to qj. So that's exactly what it is. Identically. Okay? So I'm going to... And now it comes the second term. And so what is the second term? Is a minus sign. Oops. Minus sign. And now it's the derivative with respect to qj of the same expression. Because also when I take the derivative of a square, I bring down a factor of 2. So that it gives me mivi times the derivative of vi with respect to qj. That's exactly what I have. So this is the other term. This term is this term. Now, since this is true for each I, now I can sum. From I equals 1 up to n, can sum from I equals 1 up to n. I can sum from I equals 1 up to n. Yes, sorry, this is the other n. This is this n, capital N. This is also capital N, and this is also capital N. Because I'm summing over all the masses, that means I'm summing over all the particles, for instance. Good. So what do we find? We find, let's write it here, derivative with respect to t of the derivative with respect to q dot j minus the derivative with respect to qj of something which is t. And t is going to be the sum from 1 up to capital N of 1/2 mi vi squared. So in other words, who is t?
The
Who is
kinetic,
this quantity t?
The kinetical energy.
Exactly, it's the kinetic energy. Kinetic energy. So you see, the right-hand side of D'Alembert's principle, when written in terms of the generalized coordinates, is a differential operator acting on the kinetic energy. Good. So now, let's put together the two terms that we found. Okay, we found this term, and we also found the other term, the left-hand side of the D'Alembert's principle, which was, you know, this expression in terms of what we call the generalized forces. So all in all, what we have is a sum from j equals 1 up to little n of this thing that we just found, d dt partial of t with respect to q dot j, like that, if you wish, minus the derivative of t with respect to qj. And then let me bring on this side the term with the generalized forces, and this is all multiplied by delta qj equals 0, because I'm writing the right-hand side on the left-hand side, so the whole thing equals 0 now. So now this is the form of D'Alembert's principle. So this is D'Alembert's principle in terms of the generalized forces. Generalized coordinates. And now, because the generalized coordinates are independent, because they solve the constraints, they are the independent variables, that means that these variations are independent from each other. So this whole sum equals 0 is actually a set of differential equations for each of the variables. Okay, so now we have a set of little n differential equations for each qj. Okay, for each Qj. So that is important because those are the differential equations that will give us the solution to the equations of motion for our system with the constraints and everything. Okay? Now, this is still not the Lagrangian, and that is not because we have to say something about the generalized forces. These generalized forces have to have some properties before we can, talk about the Lagrangian. If the generalized forces are anything, then this is the equation that we have to solve to find the solution to the equations of motion. Okay? But now we discuss a particular example, which is very important, which is when the generalized forces derive from a potential. And we can even talk about a generalized potential. So what is a generalized potential? So a generalized potential is a potential that depends not only on the position, but also on velocities, okay? So we have a generalized potential, let's call it U, and this guy is going to depend on the positions as a normal potential, but now we're going to allow also a dependence on velocities, so that's what makes it generalized, and all the external forces can be written in this form. So there is a term that depends on the velocity dependence of the generalized potential, and then there is the usual term. So a normal potential would only have the second term, would not have the first term, okay? Now, if the external forces F depend or can be written, if the external forces F can be written in terms of a generalized potential U like this, then we can still simplify a little bit the previous equation, D'Alembert's principle written in terms of generalized coordinates, in the following way. Because then the generalized force Qj, let me just try to be as systematic as possible. Qj, remember, had the following expression. Oh man, this is I from 1 up to capital N of the forces, these forces, times the derivative of Ri with respect to Qj. That is the expression that we found a couple of slides ago. And this is the sum from I equals 1 up to capital N of the derivative with respect to time. Now I'm using this expression in terms of the generalized potential, du with respect to Ri, Vi, minus derivative of u with respect to Ri times derivative of Ri with respect to Qj. Okay, so that is nothing but using this expression in terms of generalized potential, in place of the force. Okay, that's exactly the same. Good. Now let's compute this thing. So we compute it. How do we compute this thing? We just have the sum. So the sum is still there. I equals 1 up to N. Okay, and now the first term, this first term, I'm going to rewrite it like this. Derivative with respect to time of the derivative of u with respect to Vi times derivative of Ri with respect to Qj minus derivative of u with respect to Vi, derivative with respect to time of the derivative of Vi with respect to Qj. You agree? So this derivative here acts on du dv, which is the one that I have, times dr dq, but it also has du dv times the derivative with respect to time of the rdq, which I have to subtract. So the sum of these two is the same as that guy. So these two equal that guy. Okay? And then I have the last term, and the last term is minus du dri dot dri dqj. Okay, so this guy equals this guy. Okay? Now, this equals sum from I equals 1 up to capital N, and this is the derivative with respect to t of, and what is this term here? This term here, we have seen it before. Huh? So let me just frame it. dr dq. So let's go back a few slides. dr dq. Here it is. dr dq is the same as dv dq dot. dr dq is dv dq dot. So this is du dv dv dq dot. Okay? So that's one. Now, minus, what is this thing? This is du dvi, that's exactly this term. And then I have derivative with respect to t of dv dq. That we also had before. Derivative with respect to t of derivative with respect to, what is this thing? Wait a second, I lost it. Derivative with respect to t of dr dq is dv dq. dv dq, let me just go back. Yes, dv dq. Okay, so let's come back here. No, that we leave it as it is. So that we leave it as it is. So that is d dt dvi dqj.
Yeah, I think it's an error.
You think it's an R? This term is the same. Here I'm needing something.
I'm not saying.
Yeah.
Below. It's an R,
yes. You're right. This is not a V.
Exactly.
Okay. Yes, good point. Thanks. This is an R because it comes from this R here and the use of this derivative. Yes. Okay, so that's exactly what was not a squaring. Okay. So now, yes. So now we come here. And we look at this guy, d dt dr dq. So exactly, d dt dr dq, that is dv dqj. Okay, so that is dv dqj. So this is dv I dqj. Exactly. And then there is the last term, minus du dr times dr I dqj. Yes, good. Okay. Now, what is this? Remember what u is. U is this function here. Okay. So, u depends on r depends on q and t, u depends on v, the velocity depends on q and q dot and t, and then there can be some explicit time dependence. So this second term is just the derivative of u respect to q, because the only dependence on q is through r. Okay, so this is minus the derivative of u with respect, derivative of u with respect to qj. That's the derivative of u with respect to qj through r. This is through r, but there is dependence on q in the velocities. So that's the other term. So these two guys, this and this, equals that. The dependence of u on q goes through r and through the velocity. So the chain rule says, first you take the derivative through r, and then you take the derivative through the velocities with the minus sign. And then there is this term. But the dependence on q dot is only through the velocities, because r does not depend on q dot. It's only the velocities that depend on q dot. So therefore, this term is directly derivative with respect to t of the derivative of u with respect to q dot. And now, and including the sum, because the sum is already written here. So the u is giving all this with all the sums over i's. Okay, so that is this term here. Oops, that is this term. So what we see then is that the generalized forces can be written also with the same differential operator acting on this generalized potential. And so this means that if we define a function L, which is t minus u, and we call it Lagrangian, then the equations of motion, which we found before, which is dt derivative of t with respect to q dot j minus derivative of t with respect to qj minus the generalized forces qj, capital Qj equals 0, can be written as derivative of with respect to time of the derivative of this Lagrangian with respect to q dot j minus the derivative of the Lagrangian with respect to qj equals 0. So this is when we have generalized potential. When we have a generalized potential. Okay? If some forces derive from a generalized potential, but others do not, and those, let me call them q j tilde, then the equations are going to be this term for all those generalized forces which do derive from a potential, and the qj tilde on the right-hand side to account for the forces that do not derive from a potential. I mean, clearly, this is the form of the equations of motion that are more popular. But you have to remember that if there are forces, generalized forces, which do not derive from a potential, then there is a generalization of these equations in this form. And these equations, therefore, being that famous, are called, so these equations are called Euler-Lagrange equations of motion. Okay? So that's how we derive the Lagrangian. So I'm going to stop at this point. Any questions?
No.
All right. So now, the next day, what we will do is how to obtain Lagrange's equations from what is called a stationary action principle. So we have to look for an action principle and something called the calculus of variations, and we'll see how we can derive these equations from that principle and what are the advantages of thinking, along those lines in terms of an action principle. Okay, so if that's all, I'm going to stop recording right now, and I'll see you guys, next time. Okay, thank you very much.
See you.
Thank you.
Bye.
Bye.
Thank you.
Bye. Bye.